Okay, here's the most important part of the chapter, Bernoulli's equation. Now, Daniel Bernoulli was actually one of two brothers who were mathematicians. They lived in the 1700s. They were actually rivals to Sir Isaac Newton. Daniel Bernoulli wrote an important book called Hydrodynamica. He also did some work with the kinetic theory of gases. So not as famous as Newton, but certainly made some very, very important discoveries. One of the biggest discoveries that he made was Bernoulli's equation, which related pressure to fluid speed and elevation. Basically, what Bernoulli did was applied the conservation of energy law to an ideal fluid, and he came up with a very surprising result. And that's known as Bernoulli's effect. Basically said that as the speed of a fluid increases, the pressure it exerts decreases. So this is not so intuitive, but it is the basis for things like lift. Let's go through it. Okay, this is Bernoulli's equation. You can write it one of two ways. We can write it in terms of initial and final, or point one and point two. It's not really important, how we write it out. What is important is that we're just consistent. It comes from conservation of energy because if we look at it, it's not so much the initial energy equals the final energy. It's more about the energy per unit volume, okay? Breaking down this, trying to get rid of all these little marks that I'm making. Okay, breaking it down, we can rewrite this whole equation this way. Now, bear with me because this looks a little bit complicated, but let me switch to yellow. That's easy to see. Pressure, okay, in Bernoulli's equation, pressure exists on both sides of the equation. We can move all of that to the left and basically say that P1 minus P2 is going to be the change in pressure. Now, pressure can be thought of as work, okay? Work is force times distance. But again, this is energy per unit volume, so this would be work per volume. Later on, we'll see that pressure is actually equal to work divided by volume. So that first term right there can be thought of as the work equation that we oftentimes use. Okay, let's do the next term. We'll take this term right here and this term. If I change the color, well, let me change that color, but we'll stick with that. That's our kinetic energy term right there, okay? So as the speed of the fluid changes, the kinetic energy will change. Now, kinetic energy is 1/2 mv squared. We've replaced the m with density, where density is mass divided by volume. So this gives us our kinetic energy per volume of the fluid. Finally, here's our potential energy, okay? So what this is saying here, just to keep track of everything that's going on right here, the work done by the fluid plus the change in kinetic energy of the fluid plus the potential energy change of the fluid must be equal to 0. Basically, we conserve energy. All right? And that's all Bernoulli put together to come up with this, but it has some very, very important ramifications. And again, we can think about it this way. If I want to increase the pressure, it has to be at the expense of the kinetic energy. We've got to give up some kinetic energy to increase the pressure. If I want to increase the velocity, that has to come at the expense of pressure. Okay? All right, let's take a look at this. And again, think about the equation work equals change in kinetic energy plus change in potential energy. That's really what we saw previously. Again, work is on one side. We're looking at work per unit volume. And, let me get my little annotation tool right here. You can see the work done at point 1, the work done at point 2. Work equals force times displacement. We can substitute in for the force and displacement with pressure, which is force per unit area, and area. And then looking at area times distance, that is volume. So the work is equal to the difference in the pressure times the volume. So that's where that first term comes from. Again, pressure can be thought of in this particular case as the amount of work being done per unit volume. So there's your first term right there. Oops. Gotta clear that out. Get rid of that. Again, you can go through the kinetic energy term. We're just going from kinetic energy to kinetic energy per unit volume. And then finally, the potential energy term, where we go from potential energy to potential energy per volume. And that's where Bernoulli's equation comes from. So again, think about fluid flowing through a larger pipe to a smaller pipe. Okay, the larger pipe, the velocity is smaller, so the pressure is going to be higher. As the velocity increases, we can't just take that fluid and go from a lower velocity where the kinetic energy is lower to a higher velocity without that energy coming from someplace. The energy comes from pressure, which is sort of analogous to work. We can actually see that in this right here. Now, this is not an ideal fluid. It has viscosity, so it's actually going to lose energy through friction. But let's see what's happening in this particular case. We have a big cross-sectional area down to a smaller cross-sectional area to a big cross-sectional area, okay? So at this point right here, the fluid is going slower. That means that it's going to exert more pressure. See how it's pushing this red fluid downward, okay? Then the fluid is constricted, so it speeds up. But that comes at the expense of pressure. Now, if this were an ideal fluid, and we let it slow down again, the point would come back to here. But notice this difference right here. This is actually due to non-conservative forces, viscosity, where the fluid slows down due to friction. So we don't quite get back to the original point, but again, this is not an ideal fluid. But this is a demonstration, a visual demonstration showing that Bernoulli's principle is valid. All right, so we can understand many common phenomena explained through Bernoulli's principle. Here we solve for a hole in a container. This is just conservation of energy, looking mainly at potential energy. The fluid has more potential energy up here than when it comes out here. So we punch a hole in a container, and why does it stream out with some velocity v1? Well, at the top of the container, it has no velocity, so there's no kinetic energy. But it has all potential energy. Then it goes down to this level right here where some of the potential energy is given up. That's what's converted into kinetic energy. So let's see actually the calculations as they happen here. Let's say we have a hole that's a half a meter below the water level and 3 meters above the ground. How fast does the water leave the container? Well, again, we're comparing what the fluid is doing at the top, where it's not moving to the fluid leaking out of the side. So we're going to convert, we're going to convert potential energy into kinetic energy. Now, everything's at the same pressure. So if we look at this, we will say that P1 is equal to P2. So we can subtract that out. You know, they're both at atmospheric pressure. So there's no difference right there. Again, as I said at the top of the container, all the energy is potential energy, and we have no kinetic energy. All right, that's going to be 0 right there. So again, we're talking about this top right here. And then on the other side, just change colors right here, all of that potential energy is converted into kinetic energy. And of course, our potential energy is going to drop to 0 at that point. Okay? It won't actually drop to 0, but we'll say that's our reference level. So all we need to do here is compare our initial potential energy term to our final kinetic energy term. Okay? Kinetic energy, potential energy, rho on each side cancels out. We solve for V1, and we get that half a meter down, it's going to flow at 3.13 meters per second. No surprise, this is the same velocity a falling object will have by falling 1/2 of a meter. So nothing crazy about Bernoulli's principle here. How far does the stream go? Oh, that's a physics 1 problem. You can figure that one out. I give you the math here, so if you want to check that. But again, we can see Bernoulli's principle acting on different objects. You know that across an airfoil is shaped so the air goes faster above it than below it. So there's lower pressure above than below. But we also see the same effect on spinning objects in a process that we call the Magnus Effect. Now, if the fluid is flowing faster above the golf ball than is below the golf ball, we have lower pressure above than below. And this will cause the golf ball to move laterally, okay? Again, another example of Bernoulli's principle. That's why curved balls curve. And again, here's what I was talking about before. We look at this, and again, we have a higher velocity, so there's going to be a low pressure. Here we have a smaller velocity, so we're going to have a higher pressure. That's Bernoulli's principle. With higher pressure below than above, that results in lift. So, very simple demonstration of how Bernoulli's principle creates lift. There's also Newton's third law going on here, because as the fluid is forced at a higher velocity above the airfoil than below the airfoil, it also pushes the air downward. So for every action, there's an equal and opposite reaction. Okay. Here's a calculation. Again, the airflow stream doesn't actually look like this. More accurately, the air would be forced down after going through this. Let's say we have an airplane wing with a total area of 4 meters squared. It's designed such that at cruising speed, the air above the airfoil goes 245 meters per second. The airflow below the airfoil goes 222 meters per second. Find the mass of the plane if the lift from the wing balances against the weight of the plane. Okay, so what do we have to do here? We need to calculate the total lifting force of the wing due to this difference. So we go to Bernoulli's equation. Looks complicated, but the nice thing here is we can get rid of some of these terms. I'm always happy when I can get rid of some of these terms. There's no potential energy term here, so we can get rid of those. We're going to solve for the difference in pressure above and below the wing, because that's going to give us our lift. So that's going to be P1 minus P2, the pressure below minus the pressure above. And that comes from the kinetic energy terms. We see that the difference in pressure after going through everything is 6,912 pascals. Okay? There's my difference in kinetic energy per unit volume. The density of air is 1.29 kilograms per meter cubed. Put all the numbers, we get that difference in pressure. Now that I have the difference in pressure, I can use the area. Pressure is force divided by area. I can use the area and find out the lifting force. Okay? Difference in pressure, 6,912 pascals. The upward force, therefore, is the pressure difference times the area. We get the weight. From the weight, we can find the mass. Okay? So this plane with that surface area could take a total weight of 2,820 kilograms. Obviously, if you have more weight, you have to go faster to create more lift. Less weight, you can go slower. Ever have a big truck pass you? When you're in a car, you actually can feel the force. Well, that's because the air accelerates between the two vehicles. And this creates a low pressure. You can actually get sucked in to the airstream from the larger vehicle. So that's not such a nice thing to experience. It's a little unnerving when you're being passed by a large truck.